So thank you, Federico. You almost made me cry before starting to talk, so that would be very bad. So I want to start by thanking all the organizers of this conference who happen to be my friends also. And they asked me to start by saying something about my background. So I'm Puerto Rican. I was born and raised in Puerto Rico. I come from a middle-class family and studied in public schools. I did my bachelor's degree and my master's degree in the University of Puerto Rico at Rio Piedras campus and the PhD at Cornell University. And I have many interests. I love mathematics. I enjoy mathematics research. I love teaching. I enjoy working to promote the advanced degrees in science among women and minorities. I work also for social justice, and I have many hobbies. And during my career or my education, I have many doubts. At the beginning, I had no idea what to study, so my career has been a series of accidents, and many of them lucky accidents. So they turn out to be good accidents. I have no idea what to study, so I came to math thinking that I was going to do computer science, but I didn't like computer science, and at the end, I ended up working in a computer science department. So I have no idea what to do after graduation. So every time in my career, I've been improvising without the final goal or a big goal in mind. Then after I graduated, I have no idea if I wanted to focus on doing summer programs or devote myself to teaching or to research. But everything that I have been doing, I know that I have been taking the right opportunities at the right time. One big moment in my life, and those are those pictures there, was during my sophomore year at the University of Puerto Rico. There was a huge student strike, and the university was paralyzed for 4 months, I think, and that changed my life. That gave me a purpose. And I knew that I wanted to study math, and I wanted to study math to teach math at that time, no? And that was going to be my way of serving Puerto Rico and serving my community. And things have changed a little over the years. So my path that I took was that after I graduated from the master's degree in 1988, I taught at the University of Puerto Rico, so I changed. No? Now, instead of teaching in schools, I love the university, so I wanted to stay there, and I taught there for 3 years, but almost 3 years, but I was not going to be able to stay there with a master's degree, so I was convinced to continue to a PhD program. And at that time at the university, I was involved in some educational projects. Then I decided to continue and do a PhD, and I did it at Cornell University. And I have some people that I met there. Jesus, ¿dónde está? Some people that study with me. And of course, I work on research there, and my area was Grosvenor bases and applications to coding theory. And then when I was studying at Cornell, I met at some point Herbert Medina, and Herbert was co-directing their summer program, the MTBI program that was at that time at Cornell. And Herbert proposed to do a summer program similar to that one in Puerto Rico, and I said, yes, why not? And then we decided that the perfect place to do that was at the University of Puerto Rico at Humacao. And I had a fellowship from Rio Piedras, so I was supposed to go back to Rio Piedras, but I decided to go to Humacao to start this summer program that ran for 5 years. And there are several students from that program. Edgar is around here. I saw also Amelia. Where is Emilia? Emilia, ¿dónde está Emilia? So some students that are now faculty members in some universities. You're going to listen to Edgar tomorrow. So we did the summer program at Puerto Rico. It was a very successful program. And after the program was done, then I was looking for something else to do, and then Ricardo Cortez suggested that we work trying to improve and increase the mathematical activities at the SACNAS conference, and we worked for that for some years. And then in 2007, Ricardo also came with the idea of starting a summer program at MSRI with a group of 5 directors. There was Herbert again, Ricardo, Dwayne Cooper, and Susan Weeks, and we started the program, and I worked there for several years until 2015. And then also during that time, I started working again in education programs. So in a period of time, I worked in the 3 areas that I really like. At some point, I thought that I had to decide for one of them, but at some point, I worked in the 3 of them, and then realized that it's hard to do them all. So I start going back again, and I have devoted to research in the last years. And this is a research overview. I want to show you this to show you that sometimes you think that your research is done, is complete, but that's not true. So the topic that I researched when I was an undergraduate was Costas arrays, but for my master, I work on the composition of permutations over finite fields. Then in my PhD, I work on recurrent relations on arrays and applications to coding theory. But then after the summer programs I was done with the summer program in Puerto Rico that I started again on research after a few years, I work on interleaver for turbo codes, and that is another thing that permutations. So I start working again in something similar to what I did for my master's degree. And actually, we used the work that I did for my master's degree to construct interleavers. Then I was introduced to the area of exponential sums and study p-divisibility of exponential sums. That is a topic that I'm going to be talking about today. But at some point, my former advisor presented a problem that has applications to digital watermarking. And when I saw the problem, and when he told me that was a generalization, something for sequences, I realized that the work that I did for my PhD, that I haven't looked at it in years, had applications there, and that could solve that problem, and actually did solve that problem. We used the work that I did for my PhD to then work on linear complexity of arrays. And then recently, I went back to permutations again and work on involutions of finite fields with several students, and one of them is here. What is Lilian? Lilian Gonzalez is working also in involutions of finite fields. So with this, I mean that you never know. You never know what you're going to be working on research, and things that you think that are done are not necessarily done. New things come. So to summarize, it's good to have a plan. So what I said is, don't follow my path. Don't do what I did. I had a lot of luck. I worked hard also, but don't do what I did. Try to have a plan. But if you don't have a plan, it's okay. So there are many opportunities that will come. It's just a matter of you taking advantage of them. It's in the middle of your work. You need to change plans. It's okay. But it's important to complete the projects that you already started. And it's okay to have doubts. It's important to get out of your comfort zone, and it's important to challenge yourself and have high expectations. And at some point, you need to prioritize. I was talking to a few minutes ago, and I was telling one of our former students that you at some point need to prioritize and focus on something to be able to finish that and then come back to the other projects. And in any case, you have to work hard, really hard. And as I said, the research is never complete. You finish parts of it, but maybe some other projects will come that have relation to something that you have done before. And I love to work with other people, and I'll show you soon something about this too. And be nice to your peers and to your colleagues, because you never know with whom you're going to be ending working with. So let's go to the talk, no? So one of the reasons that I chose this particular topic was because it reminds me how important collaborations are and how fun is work with people that you sometimes meet or even have arguments with, but then you come back and work together with them. So the one on the top was my advisor for undergraduate research and for the master's degree. That's Oscar Moreno. He and Carlos Moreno were the ones that introduced the concept of the coverings that I'm going to be talking about today. And I was not involved in that type of research when I worked with him. The other two, that's myself, and that's Francis Castro. Francis started working with Oscar Moreno in exponential sums, and is the one that introduced me to this topic a few years ago. And the one in the bottom is Luis Medina. Luis was, and you see the picture right there, when he graduated from his undergraduate degree in the University of Puerto Rico at Humacao. Luis was one of my undergraduate students, and now is one of my colleagues at the UP at Rio Piedras, and actually is one of our collaborators on research. So it's amazing to have 3 generations of Puerto Rican researchers that were teachers or friends in school, and then end up working together. So that's very nice, very exciting to work. And the other thing that I like of this topic is the knowledge transfer. So what I'm going to show you today is a research that has developed, and it's interesting to see how the math that we develop has some applications, and the same applications suggest ways to go back and work more in the math, and then go and apply it again. So all this connection that knowledge transfers in between math and the applications. So the big goal that I have today, and with this research that I'm going to be presenting to you, is to provide elementary methods. We like to look at problems, and maybe problems that have been already solved, and look for simpler ways to solve the same problem. And in the process, you might generalize what you have or improve the previous results. And this is something that we enjoy a lot. And so what we do is to provide elementary methods to study the p-divisibility of exponential sums. And the methods in exponential sums usually require deep results. And we try to provide then the proofs with only elementary methods, and these are concepts or results. And this is what I want to show you today. And I'm going to be doing this in a different way. I think usually in a math talk, what we do is we do give an introduction, we give some preliminaries, we give our results, and maybe if there is time, we show the applications, no? Well, in this talk, I'm going to start with the applications. So I'm giving the introduction now, and I'm going to say a few words, and I'm going to start with the applications, then go back to the theory, and then go back again to the application, and then generalize. I will start with a finite field with 2 elements, and then generalize things to a finite field of characteristic P. Okay, and I said there, if there is time, yes, it's going to, I hope I have the time. So I'm going to start with the applications. The applications of this research are applications to coding theory and to cryptography, but also to determine solvability of system of polynomial equations over finite fields. And coding and cryptography are areas of communications, no? So when you have storage or transmission of digital data, that's what we call communications. And coding and cryptography are sometimes confused, but it's because they are very close to each other, but they have different purpose. The methods are very similar, but the purpose are different, no? In coding theory, you want to make sure that the information that you're sending or storing in a channel gets to the other side as it is, no? So there are, and in the transfer of that information in that channel, there are errors that might occur accidentally. And what you want, instead of trying to create the perfect channel, is to encode the information in such a way that even though there are errors in the transmission or in the storage, you can recover the information because of this codification that you did to the original message. In cryptography, what you want to do is to hide the information so that when you transfer the information, if there is someone that is not supposed to see that communication, they cannot get it. So you want to create confusion in the message so the intruders cannot get the message. And often you use them both. You need to protect the information from the errors and also from intruders. And the methods, as I said, are similar. And one object that is used in these areas are Boolean functions. By Boolean functions, we mean, let's see if I can use this. Well, can you see the green dot there? So our functions are evaluated in vectors of zeros and one, so n tuples of zeros and one, and the function returns either 0 or 1. So you evaluate that in a vector of zeros and 1, and you get 1 or 0 as a result. And any Boolean function can be identified with a polynomial in n variables. Any Boolean function that is with this domain can be identified by a Boolean polynomial that where the exponents are either 0 or 1. So you either have or not have the variable present in that polynomial. And one property that is important for the applications, especially for the cryptography applications, is that the Boolean functions are balanced. So you're using Boolean functions and you want the information to be hidden, no? So you don't want biases. So you want that when you evaluate the polynomial, you have the half of the values to be 0 and half of the values to be 1. Half of the results to be 0 and half of the results to be 1. So you don't have a bias towards one or another. One of the first codes that was invented were the Reed-Muller codes. And the Reed-Muller codes actually are also very useful for cryptography. Many of the properties used in cryptography are studied in Reed-Muller codes. And even though these codes are very old, there are still many open questions related to them. And to define Reed-Muller codes is very easy. We're going to take a Boolean function, and we are going to evaluate that function in all the tuples, n tuples, binary n tuples. And for that, of course, we order the tuples with respect to any order. You choose an order, and you order the tuples in that order, and then you construct a vector with the results. So you have a vector of length 2 to the n with the results. And of course, the results are going to be 0 or 1 because it's a Boolean function. And now it's the set of these values given by polynomials of certain degree or certain degree or less, those are the Reed-Muller codes. So I'm giving you the way that the code is defined, also the set of code words is defined. I'm not telling you how to encode or how to decode. So the kth order Reed-Muller code of length 2 to the n is going to be the set of vectors that you obtain by evaluating, so for each function of degree less or equal to k. So as I said, you evaluate the function in all the tuples, the 2 to the n tuples, and you get a vector, and the set of all these vectors given by polynomials of degree less or equal than k, that's a kth order Reed-Muller code, okay? So to study the Reed-Muller codes, people just organize them in certain ways, and they study cosets of Reed-Muller codes. And for example, you can obtain a quotient of Reed-Muller codes by taking Reed-Muller codes of different degree, of different order. For example, here we have the quotient given by the Reed-Muller code of order 3, modulo the Reed-Muller code of order 2, and the cosets have this form. So our polynomials that have degree 3 plus any other polynomial of degree 2 or less, okay? So these are the cosets. And by organizing this, you can study many of the properties of the Boolean, of the Reed-Muller codes by just choosing the right cosets and the coset representatives. And there is a study that was done by Cusick and Cheon on balance function that they study the cosets and the quotient of this Reed-Muller code, and they chose representatives for each coset. And it happens that if the balancedness of the polynomials in that coset is preserved. So if you have, so the coset contains either all balanced functions or no balanced functions. So just to study one representative gives you its complete set of balanced or non-balanced functions. So they construct this table computationally. And if you look at this table, they have the coset representatives, and they counted the balanced functions in that coset. And most of them has 1.8 or 1.7 million of Boolean functions. But there are two cosets that have zero, balanced functions. There are two cosets that have zero balanced functions. And of course, they were looking for balanced functions, so they didn't want to look here because there are none. But they were surprised of why is this big difference? Why do you have so many balanced functions here and have none? Of course, you know that if you have one, that all the members on the cosets are going to be balanced or not balanced. But they were very surprised. They were expecting to have some balanced functions in in each one of the cosets, and they could not explain that. So by the time that we look at this paper, we have already finished one of our papers with the covering method, and we saw this, and we look at those coset representatives, and immediately we said, of course, these representatives contain a minimal covering, and it's a unique minimal covering. And because of that, there are no balanced functions there. So with this method that we were using, we have a very good intuition of what was going on. And of course, when you're studying Boolean functions for cryptography, you're looking for functions that are balanced. But knowing which are not balanced is useful too, because if you're doing computational search, you can eliminate these two cosets right from the beginning, no? And so we start then working on trying to describe which were the characteristics, so we can a priori say which coset you don't have to look at. So let me now, so this is what I just said. These monomials give you a covering for the polynomial. Of course, I have not told you what a covering is because I told you that I was going to give you first the application. So this justified me defining what covering is. But this is the reason why these polynomials were so special. So let's see now. So we know what the Boolean functions are, and they have very nice properties. Now I have some notation. When I use bold X, I might mean a monomial with all the variables, or I might mean the tuple of all the variables. And it should be clear from the context. And what happened is that the Boolean functions have very nice properties. If you have an exponential like this one, so this is a primitive root of unity in F2. So if you have this exponential, it's the same as a monomial, as a binomial. So you can change an exponential for a binomial as functions, they are the same. If you evaluate this in 0, if some component of this monomial is 0, then you have 1, and same happens here. And if it's all ones, then you will have here -1, and the same happens here. So these are the same thing as functions. And the other thing is that any variable that is raised to a power is going to be exactly as the variable itself as a function, no? Because you will have either 0 or 1. You're going to be evaluating in 0 or 1. So with this, we can then study the exponential sums and change them to polynomials and then study these Boolean functions. And as I said, the balanced functions are the ones that give us half of the value once and half of the value 0. So the exponential sums, what are the exponential sums? So with any polynomial, and here I'm talking about polynomials that are defined over F2 in tuples of just zeros and 1. So what you do is that you associate a number to a polynomial, and that number is given by this. You are going to be taking, you take -1 and raise it to the polynomial, and you evaluate that polynomial in all the tuples. No? And that each term is given by -1 raised to that evaluation. So you are going to be, and remember that these are Boolean functions, so this exponent is going to be either 0 or 1. So you're going to be adding -1 and 1. So with this, if you have that half of the values are 0 and half of the values are 1, so half of the terms in this sum are +1 and half of the terms are -1. So this exponential sum gives you 0 if and only if the function is balanced. So this is a way to know if the function is balanced. Of course, it's not too helpful just with the definition because it's the same work to determine if the exponential sum is 0 or than it's of balance. But there are many tools to study exponential sum that we can take advantage of to study then the balancedness of the function. And the two-divisibility is one of them. So when I talk about two-divisibility, I'm talking about powers of 2 that divide the exponential sum. And when I talk about exact two-divisibility, I mean the highest power of 2 that divides the exponential sum is the 2 values. So that means that, for example, the exact two-divisibility is A if 2 to the A divides the exponential sum, but then 2 to the A plus 1 does not divide the exponential sum. Okay? Of course, this might not exist because if the exponential sum gives you 0, then you don't have the highest power of 2 that divides because 0 is divisible by everything. So that means that if you have exact divisibility, two-divisibility, do know that the exponential sum is not 0 and therefore is not balanced. So this is a way to know if a Boolean function is not balanced, if you have exact divisibility of its exponential sum. So some applications of this are the following. So if sometimes you don't have exact two-divisibility or you cannot compute it. But if you have good bounds in the two-divisibility, that this has applications to the covering radius of the codes, and the covering radius gives you information about the error correcting capability of the code. You can also have better bounds on the non-linearity of the function, and the linearity of the function is a property that is related to the application. It's important in the applications to cryptography because if a function is highly linear, is close to being linear, it's a simple function. So you want to have higher non-linearity to have a function that is good for cryptography applications. You get better bounds for Hamming weights of Cosets of Reed-Muller codes and some other problems related to coding and cryptography. But if you have exact two-divisibility and you are able to compute exact two-divisibility, or at least know that it has the function has exact two-divisibility, then you can determine if a system of polynomial equation is solvable or not. And I'm going to be talking about this application later. And in the case of balanced functions, as I said, if you can compute exact two-divisibility, you know that the function is not balanced. So that means that you can just forget about that function for an application to cryptography. It's a way to eliminate functions and look in other places. Okay, so let's see finally what the covering method in F2 is. So as I said at the beginning, the covering method was introduced by Oscar Moreno and Carlos Moreno, and I forgot to take note of the year, and I don't remember, was in the 70s? No, I mean in the late 80s, And for a covering, what they use is you have coverings for polynomials. So you take a polynomial and you consider all the monomials in that polynomial and you build sets. And a set is a covering if the monomials in this set have all the variables that your polynomial have. So for example, here we have a polynomial in 4 variables, and we can construct different set with the monomials. But if you look at the monomials here, this is the only one that has x3 in it. So for a covering, you will need this monomial. And then the only variable missing here is x4. So to complete the covering, you can just choose this other monomial or this other monomial, and you construct 2 different coverings. And of course, you can add the other monomials in the polynomial, and you will still have a covering, but you're looking for minimal coverings. We're looking for minimal coverings. So we want the coverings that are smallest in size. Yes? No, thank you. That's a very good point. So the polynomials that we consider need to have all the variables that in the ring that you're working on. That's a very good question. Thank you. So the polynomials contain all the variables, and but not all the monomials contain the variables, so you build sets of these monomials. So in this case, these 2 coverings are minimal. You cannot construct smaller coverings than these 2, but there are others that have higher, larger size. And one thing that I want to point out, and this is something that we noticed when we were trying to generalize this to characteristic P. When this was presented in this way. But look at this. If you multiply these 2 monomials, then you obtain the monomial that consists in all the variables, no? Because x1 to the 2 is the same as x1, as I was saying before, as a function. So if you multiply these 2 polynomials, you get the polynomial with all the variables, and the same happens here. So that's another way to look at coverings. If you multiply all the monomials, you get a monomial with all the variables. In the generalization, you will want this, but then you want the variables raised to the characteristic -1. But in this case, the characteristic is 2, -1 is 1. So that's why when they look at this at the beginning, they were just counting monomials because it coincides. And it took us a long time to realize that we have to see this in this other way to be able to generalize this. Okay, so as I said, the Moreno introduced the minimal coverings to give approximations of the 2 divisibility of the exponential sums. And this is the theorem, and this is the year, 1994, was later than what I thought. So, so if a polynomial has a minimal covering of size, whatever size it is, then 2 to the size of the minimal covering divides the exponential sum. So this is a bound on the divisibility, and with this we cannot get exact 2 divisibility. And for the applications that we were looking at that moment, Francis and I that started working with this, we wanted to determine which sets of polynomials, which system of polynomials have exact 2 divisibility, because we wanted to answer questions about solvability of polynomial equations. So this was not useful for us. So we started looking at the proof of the theorem to see if there we find an answer to be able to improve this and find and compute exact 2 divisibility. So remember that I told you about this property. -1 to the x is equal to this binomial. So what we do is that, or what they did, is to change the exponential sum to a sum of just, to a polynomial. To a polynomial. They change, so you have -1 raised to a polynomial, so a polynomial is a sum of terms, so we have here -1 to a term times -1 to another term, and each one of these factors can be changed to these binomials here. And if we expand this, we get 2 to the n plus some other terms. And then the two divisibility of the exponential sum is determined by the two divisibility of these other terms. Now let's study the two divisibility of these terms. It happens that we have here factors of 2, and this power over here is the number of monomials that are involved in that term. So look at this. This binomial here, the monomial that appears here are the monomials in the polynomial. So when you expand this and you combine this, if you count the number of monomials that are involved in that term, then you have a power of -2, and this other polynomial here happens to be equal to 2 to the L, and L is the number of variables missing in the combination of these monomials. So this, here you have a combination of this number of monomials, and the number of variables missing is this exponent here. So the two divisibility of any term here is given by the sum of the monomials that were involved in that term plus the number of variables that are missing. And this is related to the covering, because in the covering, we were looking to cover all the variables, which means that we have 0 here. And with them, if it's a minimal covering, this is going to be as small as possible. Of course, you can have other, the divisibility of some other terms that is also small or even smaller than, actually not smaller, but it also with the same two divisibility with a different combination, where you might have some missing variables and a smaller number of terms here, but we try to avoid those. And this is one of the conditions that we have in the theorem. So what happened is that, to illustrate what's happening, so this is the exponential sum expanded, and suppose that these two terms have exact divisibility of 2. This term over here is 2 to the 2 plus times another term that, another factor that is odd. And this one is 2 to the 2 times another factor that is odd. When you add these two, then your divisibility increases. And this has other type of divisibility. So that means that if you're adding an even number of terms with the smallest, with the minimal divisibility, then your divisibility of the polynomial increases. So that's the problem. That's why Moreno and Moreno just gave a bound given by the minimal coverings, because the divisibility can go higher depending on how many coverings you have. So what we did, well, let's count then the number of minimal coverings. And but also we need to avoid what I said, and we need to avoid the cases where you have minimal, smallest divisibility given by things that are not minimal coverings. And the way to avoid that, it's very simple to say, okay? Which is just having the covering that each monomial in the covering contributes at least 2 new variables. And I'm going to show you an example of what this is. With this, we avoid the case of having other terms with small divisibility that are not coming from the minimal coverings. And then for the other, you will only have minimal coverings contributing to the divisibility. And if the number of minimal coverings is even, then the divisibility is going to be higher. If the number of minimal coverings is odd, then you have exact to divisibility. And this is the example. Let me show you, first telling you that in particular, when we have exact divisibility, we know that if we have a Boolean function, we know that the exponential sum is not 0, so the function is not balanced. And also in the case of the application of solving system of polynomial equations, we know that then the system is solvable. And we'll see this later. So let me show you what the conditions are. You remember the problem that by Cusick and Cheon in the table that I showed to you? So this, if we are working with 6 variables, this forms a covering. is a minimal covering no matter what function you have here. Because here you will have polynomials of degree less or equal than 2. So to cover all the variables, you will need more than one monomial. So you can take this out and substitute it by monomials here, but then you will need at least 2. And so the minimal covering is going to be this one. So we cover all the variables. And we're covering all the variables for any polynomial in this coset. So this is going to be a covering. And also, each of the elements in the covering contribute, actually not 2, 3 new variables. So we have here that the variables here are not included here, and the same here. And actually, the same covering works for the other polynomial. And so this is how, when we look at this, we realize, of course, this has unique minimal covering, and the whole coset, any polynomial in the coset cannot be balanced. So the result that we have for that just said when I explained the problem is that we can obtain an improvement to Moreno and Moreno result by just adding an extra condition of having that the covering, each polynomial in the covering contributes at least 2 new variables that are not contained in the other monomials. So if the size of the if the number of minimal coverings is odd, then the divisibility is exactly the size of the covering. And if the number of minimal coverings is even, then the divisibility increases, but we don't know how much. So maybe we have to put some extra conditions to try to control that, but that's very hard. We have tried to control that other part, and we, in other cases, we just can say that the divisibility is increased. And from here, we can see that when this is an example when we improve Moreno result on divisibility. We don't have exact to divisibility, but we improve it. And in the applications, a small increase in the bound for divisibility is a huge, is very important. It's very useful. Okay, another thing that we use, and I have mentioned it, I'm going to go quickly over here, is that what we work in the application of the coset is deformations of a function. So we were choosing coset representatives, but then we were adding any function, no, in the code that we were modding out. And what we are doing is selecting a function and deforming the function with other polynomials with certain characteristics. And here what we did was just to formalize what we saw in what we saw in the application to the math. No? So we have a theorem that has the result as a math, as a general thing, not as in the application of just the Reed-Muller codes. So for the application, as I said, this result explains the uneven behavior noticed by Cusick and Cheon, and I'm not going to go over the details, but this is what I have explained, that if you have minimal covering with polynomials monomials that contribute at least 2 new variables, you know that that function is not balanced. And that's how we can explain this. And then we start looking for other conditions to generalize these conditions that we saw specifically for those. And then you can get lots of different conditions that you can set where you can satisfy the conditions for the theorem that what we found, and those conditions then help you to determine a priori cosets that are not balanced in other cases. So it saves you a lot of time in computation. Okay, so at least I want to give you the idea of how the relation of the application to the theory went. So we start with the theory. No, we work on that. We saw the application. Then the application, we realized that we can answer those questions, and then we develop some more theory. So we were always thinking in doing something similar to the covering method, but not for the binary field, just for fields of any characteristic. And we, of course, the first thing that we need is to define covering in this case. And this took, not only that, okay, 5 minutes. You stole some minutes from me. Okay, so let me go fast here. So we have, again, exponential sums. And what we have here as the base is a pth root of unity, and we can define the exponential sum in a similar way. And also Moreno and Francis Castro and Chuman Kumar have a result for the divisibility, or bound on the divisibility of exponential sums over finite fields of characteristic P. And I should say, the coefficients here are in FP, in the base field, okay, in the base field. The ones that I'm talking about here. And what they did is that they construct a system of congruences. And the columns here come from the exponents of the terms. Each row corresponds to a variable, okay? And so we were trying to find a definition for the covering for this other case. And we start going around it, and we realized that we can write that system of congruences as a system of polynomial equations. And if we look at it in this way, what are we doing? We are taking the exponents of the terms, multiplying by a variable, and what we are looking is for the smallest vector of variables. So these are unknowns. The smallest vectors of vector here, such that this gives us multiples of p minus 1. So we are looking for p minus 1 coverings when we look at this in this other way, because we are here, these are the exponents, so is this the same as raising the monomials to v sub 1, the first monomial to v sub 1, etc. So it's the same as if we take the monomials and raise them to powers, so we obtain multiples of p minus 1. And this is exactly what happened in the characteristic 2 case. The thing is that the exponents were equal to 1, and we were not seeing this. So the definition for a p minus 1 covering then is a set of polynomials. A p minus 1 covering for a polynomial is a set of monomials in the polynomial, such that you can cover all the variables, but with multiplicity that is a multiple of p minus 1. Okay? And here is a quick example. So we have a polynomial in 2 variables. So if we choose this monomial, we have the 2 variables. And we want, here this is over F7, so we want 6 divisibility, and 6 covering, I'm sorry. So if we just raise the monomial to the 6, that's a 6 covering. And if but we can also take this monomial and raise it to the 3rd, and this one to the 2nd, and we have another 6 covering, or maybe this one to the 2nd, and the first one to 1, and we have another 6 covering. And the size of the covering is the sum of the exponents that you're taking. So this covering has size 6, this one has size 5, and this one has size 3. So this is the minimal covering of this polynomial. So we were able to generalize that. And I'm just going to say, I want to say something at the end, so I'm going to jump all the theory. We generalize all the results for characteristic 2 to characteristic P, just for the base field. And of course, things get a little bit more complicated, because instead of counting how many coverings, we need to take into account the coefficients now. And it's a little bit more complicated, but it's not too hard. And we have then similar results, but this is for the base field. We are now, and the applications are applications to solving systems of polynomial equations to finite fields that are deformations. So we have similar results for system of polynomial equations that to determine when the system is or is not solvable. And the current work is generalizing. Actually, we are just writing this up, generalizing this to Q minus 1 covering. So that this completes the covering method for any finite field. Now, the problem is that the statement of the results are elementary, but the methods to prove the theorems are not elementary anymore, so we need the heavy machinery. So we kind of, but it still has the intuitive flavor on it, and some of the examples show that. And I want just to finish, give me 1 more minute. Today is a special day. It happens that my talk is on the International Women's Day, and here's a sort of a chronology of different events that gave rise to this day. And many people think that it's because some particular event that occurred in March 8th some year, but it's a series of events. And so things have gotten a lot better for women, but still in 2018, the struggle for equity continues. And this is especially true in math. No? In mathematical sciences, the situation is terrible in the degrees. So this chart, this is a very recent chart that shows the percentage of women having bachelor's degree in the math sciences. So it's almost half, 50%, so that's fine, no? It's close to the population. The master's is less than that, but then when we go to PhD, in 2014, so this is about 30% of the PhD went to women, so we are still being behind this. And when we look at the statistic for Latinas and Latinos, and this is just bachelor's, in science, this is worse. The line for math and statistics is this one over here. And of course, this doesn't say anything if you don't compare this to the percentage of Hispanics in the population. So this is close to 7% or 7.5%. And the population of Hispanics in the US is 18%, so we are behind. And since today's Women's International Day, I want to mention an association that is trying to work towards the equity in this area, that is the Association for Women in Math. And we need to increase the number of Latinos and Latinas involved in the AWM so we can give ideas of how to improve the situation for Latinos and Latinas in math in general, but specifically also for women, Hispanic women in math. So if you're interested, go to the website, make suggestions, and get involved in this and SAGNAS and this conference and anything that you can. Okay, so thanks. One more. What is it? ¿Qué pasó? Thanks. Thanks to the organizer and to you for listening.